Three big questions were occupying Kepler's astronomical mind, and his mind was convinced there must be three good answers. He only needed to find them. Why are there 6 planets and not 5 or 7 or whatever? And why are they placed at their distances, and why do they move as they do? He knew the planetary distances from the Sun as calculated by Copernicus by heart, and had been playing all sorts of number games with them, but all in vain. Until that magic Friday, July 19, 1595. In an almost empty lecture room, Kepler was teaching astronomy. In particular, the so-called Great Conjunction, when Saturn and Jupiter appear very close against the background of the stars of the zodiac. Starting from such a conjunction, he explained that both planets orbit the Sun in the same direction. Jupiter in about 11 years and 10 months, while Saturn took much longer, about 29.5 years. He showed how you can calculate that the next conjunction will be after 19 years and 10 months, when Jupiter overtakes Saturn again, even before Saturn finishes its first round, at 242 degrees. With the same reasoning, the next great conjunction would be here, and the next here, close to where we started, but not exactly. And so on and so on. And he saw that this drawing created another circle with about half the diameter, while Jupiter happened to be half as far from the Sun as Saturn. The answer was not in number games, but in geometry. He needed a second revelation to really get there. The conclusion in his first book, Mysterium Cosmographicum, that would be printed only 1.5 years later. That conclusion would turn out wrong. But I dare say that this day was the watershed day that drew Johannes Kepler's mind definitely from the pulpit to the heavenly skies. And Mysterium Cosmographicum would be the first of many groundbreaking books that would follow. In the preface, he describes his struggles to make sense of the planetary orbits, how he saw the splendid harmony of things in rest, God, Jesus and the Holy Spirit, concluding there must also be harmony in what moves. How he noticed that orbit velocities consistently decreased with orbit size, and somehow in proportion. So there must be some basis for the orbit sizes as well. I guess he struggled particularly with a large jump in distance to the Sun between Mars and Jupiter, a factor of about 3.5, much more than between Jupiter and Saturn. As a way out, he postulated a small planet in between Mars and Jupiter, but even then he could not get a satisfactory build-up. Funny enough, one later discovered a whole asteroid belt and a dwarf planet, Ceres, between Mars and Jupiter. He then describes another attempt to make sense of the distances and orbit velocity with this diagram, with the Sun, the fixed stars, a quadrant, and the distances of the planets on the vertical axis, where the length of the horizontal line to the quadrant would represent, listen carefully, the motive power of the Sun. Eventually, he rejects this approach as well, but that remark is revolutionary. No mechanical clockwork as a machine put or kept in motion by the Creator, but an active role of the Sun in determining the motions of the planets. That idea was totally new, and as we now know, totally correct. It was not Newton, but Kepler who was the first to see that, an often overlooked fact. He lost almost a whole summer on these efforts, until that famous day, July 1995. So impactful that he explicitly mentions that date. Note that he says 9/19 July. This is a manifestation of the calendar reform, as we discussed in the previous episode. In Graz it was July 19, but in his homeland Württemberg it was July 9. So, if a triangle defines Jupiter into Saturn, would a square define Mars into Jupiter? No, it didn't. What followed was another fruitless play with polygons, with on the background the mystery: why are there 6 planets revolving around the Sun? Why 6? Here, 2 reasoning lines merge into one fantastic idea. The July 19 epiphany brought his minds into seeking it in geometry rather than in plain numbers. And the 6 questions brought the 5 regular polyhedra, also known as Platonic solids, on the table. In 2 dimensions there are an infinite number of regular polygons: triangle, square, pentagon, hexagon, heptagon, etc., etc. But in 3 dimensions there are only 5 regular polyhedra, as already proven by Euclid almost 2 millennia before Kepler. There's a fixed ratio in the diameter of the circumscribed circle and the inscribed circle of a regular polygon. For an equilateral triangle it's 2, as he drew on the blackboard. For square it is about 1.4. The circumscribed and inscribed sphere of a regular polyhedron also have a fixed ratio. For example, for a cube it's about 1.7, roughly Saturn versus Jupiter. And for a tetrahedra it is a factor 3, roughly Jupiter versus Mars. Dodecahedra, Earth. Icosahedra, Venus. And finally the octahedra, Mercury. The distances seem to match the orbit sizes of Copernicus. And there you have the full plan behind the planetary system, the reason for the 6 planets and their relative distances to the Sun. Imagine his joy and excitement to be the one that saw God's plan, and his haste to write it all down in a book. What we discussed just now he described in the 5-page preface of the book. The whole book counts a good 180 pages. 100 pages for dedication, an appendix by Michael Mestlin, and a reprint of a clear explanation of the Copernicus model, Narratio Prima of Joachim Ritschus, as Mestlin had suggested to add. That still leaves 80 pages for the actual book. Where did he need that 80 pages for? Well, dear viewer, if you permit me to say, God is in the inside, but the devil is in the details. One small detail that he thought about: why this order of polyhedra? He must have been staring at these numbers 6, 4, 12, 20, 8 to find a pattern. In the end he satisfies himself with that these are the primary figures consisting of squares, triangles and pentagons. Then there's Earth, and what follows is more complicated constructions of the primary polygons. More importantly, Kepler had to carefully fit in all planets with the Copernicus data. And you run into a bit of a problem if you put the Sun in the center of everything, knowing that all planetary orbits, still assumed spherical, need an off-center position of the Sun. And each planet had their own amount of off-center distance. Also, he followed Copernicus with epicycles to describe speed variations. And this all led him to give each planetary orbit a width. And a lot of work went into calculating these widths. But in all his writings on these matters, it shines through that he didn't believe in epicycles as a physical reality. He believed that the planet was just moving within that width, guided by the motive powers of the Sun. He makes that explicitly clear in the chapters 20 and 22 of the book. They contain mistakes, as he later admitted, and are written in a rather cumbersome way. He kind of had to, because our modern approach with algebraic equations was just about to develop. That would have required way less words. But the point he makes is the crucial role of the Sun as origin of a driving force that decreases with distance. He compares it with the reduction of light intensity, but he took the force to act in a plane, which leads to an inverse dependence of the distance. If he had only made the step to 3 dimensions, like he did in going from polygon to polyhedron, he would have correctly formulated the inverse square dependence of the force of the Sun, as Newton would do 90 years later. Although the nature of Kepler's force is still a bit vague. Kepler also explains the increase of velocity of the planet from perihelion to aphelion by the increased force of the Sun, but again in a rather complicated way. We now know that the fit to his polyhedra model is coincidental, and later 2 more planets, Neptune and Uranus, were discovered, invalidating the whole concept. Had Kepler stopped thinking here, Mysterium Cosmographicum would have been seen as a curiosity, and his groundbreaking remark about the role of the Sun probably unnoticed. Kepler himself already foresaw that this was not the end of the story, as he called the book Prodromus, Forerunner. He expected a follow-up when he would be able to use more accurate data. That follow-up came, but only 25 years later, after various other groundbreaking books. Johannes Kepler did not foresee that this book would be the only one from Graz, as he would soon be indulged in private and political turbulence. Stay tuned.